Well, standing a bit far away here. Still hope you can all hear me. It's a wonderful day, and I will continue with chapter 5 in György Buzsaki's book. Buzsaki, I think the correct pronunciation. Let's give me a sec here. I need to put my goggles on. And I'll need a sip of coffee. The drink of Poincaré and Pascal. Not to be lived without. This wondrous portion that makes one's spirit shine and ideas spring to forth. I don't know if I could do it without coffee. Let's see here. So this will be 11:69 if I'm not misnoming myself here. Let me give it a check. No, 1170 it is, sorry. 1170 of the Heidegger series. And the theme is György Buzsaki. So we ended with the allocentric representation that describes the relationship of each position to any other position, a map. We were talking about that we have an internal map for matching with the external, and both are necessary, otherwise there will be nothing of space and nothing of time. I think people once upon a time was absolutely aware of that, and that's why the Newtonian ideas seem so utterly weird, because it's a gut reaction coming from Leibniz, Huygens and Berkeley. But now we're used to it. We're used to thinking or not thinking, not using our locator cells, and thereby we have no connection to reality anymore. That makes the movie, I don't really like the concept, I like the movie, Matrix, even more ridiculous. We know from a neurological standpoint we are in the Matrix in a proper way, not as depicted in the movie. We don't have contact to time and space, our own reality. A few of those, though, the ones that lead us. Place cells and place fields. In contrast to the entorhinal grid patterns, hippocampal neurons display highly flexible spatially tuned patterns called place fields. Typically in a given environment, most pyramidal neurons are silent, and the minority forms a single place field. That is, the neuron becomes active only when the animal reaches a particular location in the testing apparatus. This response is why John O'Keefe named them place cells. The size of the place fields is small in the dorsal part of the hippocampus and grows in size toward the ventral pole, in register with the grid size, increase of topographically connected medial entorhinal cortex. Because of the discrete place fields of hippocampal neurons, they carry much more specific information than the entorhinal grid cells. A large population of place cells with unique locations can provide a reliable map and a faithful track to the animal's position in the environment. Surprisingly though, in contrast to the entorhinal grid map, the hippocampal map is not static. If the animal is placed in a different environment, a different set of place cells become active. Neighboring place neurons in one environment may have a very different spatial relationship with one another. For example, a pair of place cells representing adjacent pieces of the floor in one apparatus may become silent in another, or just one of them may remain active but a different position. If both of them continue to fire, the distance between their preferred firing locations may be different in the two mazes. Thus, each environment is represented by a unique combination of place cells and place fields. Even seemingly minor changes in the testing apparatus or the variables of the task may strongly alter the firing pattern of the hippocampal place cells. The spatial layout of individual place cells, i.e. the map in here, is not related to the location relationships of place cells in the hippocampal circuitry. Two neighboring pyramidal neurons are just as likely to represent adjacent or distant patches of the environment. Instead, place cells dynamically and relatively randomly reconfigure under various conditions. Largely because of this arrangement, the densely connected hippocampal recurrent collaterals can generate discrete maps individualized to the many environments an animal visits in its lifetime. To envision such relationships, imagine that many place cells on a piece of paper are interconnected with rubber bands. When you crumble the paper, the different place cells will occupy a new set of displacement relationship to each other. These distances on the surface of the wrinkled paper may be thought of as the synaptic strengths between them. Now you can flatten the paper and crumble it again a bit differently. This gives another set of relationship. and so on. Thus, the same set of neurons can give rise to many different constellations of relationships, each of them representing a map. Of course, a map is just a static positioning tool, a reference frame in which the spatial relationships among landmarks assist in defining the animal's own location in the environment. This relationship is described eloquently by O'Keefe. Each place cell receives two different inputs, one conveying information about a large number of environmental stimuli or events, and the other from a navigational system, which calculates where an animal is in an environment independently of the stimuli impinging on it at that moment. When the animal had located itself in an environment, the hippocampus could calculate subsequent positions in that environment on the basis of how far and in what direction the animal had moved in the interim. In addition to information about distance traversed and navigational system, we need to know about changes in direction of movement, either relative to some environmental landmark or within the animal's own egocentric space. However, a map is useful for the animal only after it has already learned the significance of the relationships among the landmarks through active exploration. It should be through active explorations, I'm dead certain. As the crow flies, navigation and self-motion. Bruce McNaughton and Carol Barnes at the University of Arizona took an important step in linking the static representation of maps to animal navigation through carefully designed experiments and reinterpretation of existing data. Their first key insight was that head direction information is an integral part of the navigation system. The second insight was that self-motion is the primary source of spatial information leading to place-specific firing. In other words, visual landmarks and other stimuli in the environment gain their meaning by action. Although they did not explicitly spell out this link, several experiments support the primacy of action in navigation. First, the firing frequency of place cells depends on the animal's speed. Second, on running a track, a robust place field is observed on the left to right journey is often absent on the return run. That is, place fields are not absolute descriptors of the x-y coordinates of the environment. They also depend on context, such as which direction the rat is facing and how the head direction orients the entorhinal hippocampal map. Third, under certain circumstances, the same physical space can be represented by different sets of place cells, depending on other contextual variables. For example, when a rat is placed into an otherwise familiar environment in total darkness, new place fields can emerge and persist subsequent light. Thus, place fields can arise independently of the visual landmarks, although landmarks can control the expression of the place cells. Fourth, changing the features of a landmark without changing its position can affect the map. For example, after a white cue card in a symmetric apparatus is placed with a black one, the place cells stay put relative to the radial axis of the cylinder. However, after several trials in which the white and black cards are alternated, the place field distributions of several neurons become largely uncorrelated across the two conditions as the animal learns to distinguish the two cues. Fifth, when a rat is repeatedly disoriented by turning it by hand multiple times before placing it into a cylinder with few landmarks, its place fields tends to destabilize. 6. When the distance between the start and goal boxes changes, only a fraction of neurons remain under control of distant room cues. Many of them realign as a function of the distance from either the start box or goal box. The list goes on. The profound implications of these observations led McNaughton, Carol Barnes, and their colleagues to postulate a hypothetical path integrator system, a sort of body cues feedback supported guiding mechanism based on information from local visual and somatosensory cues, proprioceptive feedback from the body, the number of steps taken, vestibular input, that is translational and rotational head accelerations, and likely corollary discharge from self-motion activity. Integrating self-motion allows animals to move through space even though there are no prominent landmarks, while keeping track of their starting location. The path integrator system can operate without a prior spatial reference, or even in complete darkness, by calculating the distance traveled and the turns the animal made. Dead reckoning, another name for path integration, was one of the earliest forms of marine navigation. From a home base, the captain calculates the movement of the ship based on heading, speed, and time. Multiplying speed by time provides the distance traveled. The sequence of distances and heading direction changes is noted on a chart. This route chart can always be used to calculate the straight path to return home. Dead reckoning was the main navigation strategy for sailors in the Mediterranean Sea for centuries before Portuguese sailors introduced maps and landmarks, and a navigation based on that. There were not landmarks, or more specifically skymark or celestial points. Navigation by path integration is intuitively appealing. Not only sailors but also animals can find their way without landmark cues. A gerbil mom can reliably retrieve her pups from within a circular arena and return to her nest at the arena border in complete darkness, using an internal sense of direction. When the platform is slowly rotated so that the mom does not notice it, she carries the pups to the original spatial position, even though the nest is no longer there. Yet the path integration presents some challenges. Every change in speed and direction contributes to error accumulation. As each estimate of position is relative to the previous one, these errors quickly accumulate. The exact brain networks involved in path integration have been debated from its conception. Initially, the hippocampus was the suspect, based on both recording and lesion experiments. With the discovery of grid cells, the entorhinal cortex became the favorite structure. Although the majority of grid cells are present in layer 2 of the dorsomedial entorhinal cortex, many neurons in deeper layers respond to the head direction, and a subset of these neurons also show typical grid responses. The running speed of the animal correlates with the firing rate of some place cells and most inhibitory interneurons. Thus, the conjunction of positional, directional, and translational information in the same entorhinal groups of neurons may enable the updating of grid coordinates during self-motion based navigation, as the argument goes. However, such correlation alone may not be sufficient because entorhinal neurons receive information about head direction, and speed from multiple sources. In support of this idea, damaging the anterodorsal nucleus of the thalamus, a main hub of the head direction system, leads to the disappearance of grid dynamics. Furthermore, position, speed, and head direction information and even distance are present in hippocampal and the adjacent subicular neurons as well. Neurons in the parietal and retrosplenial cortex may also be involved in computing the animal's motion relative to environmental and body cues, suggesting path integration involves multiple systems. There's an example here that's very interesting, footnote, and I will read that one. A blind child who's walked from a base to three objects, landmarks, in a large room can immediately find the routes between the three objects on her own, even though she has never experienced those paths. To commute between any two targets, the child must encode the three training paths by dead reckoning, store these paths, and combine two correct stored paths to deduce a new one, a demonstration that the cognitive map can be constructed solely on the basis of dead reckoning navigation. It's widely interesting. It's just amazing. So blind people also have these maps, which is like obvious. And I remember also in the modern age people are navigating with their eyes. That is very, very detrimental to the locator cells, the place cells, for the functioning. It has a deteriorating effect. And that comes from the mistaken understanding of space. And it's just a mistake that once you are in true space, you cannot understand what it was. And it's very important to understand that Newtonian space is different from each single person. It is not even consistent within that person. Very important to remember. The very idea that Newtonian space can be shared reinforces the idea that it is actually a real conceptual space. No one in quantum mechanics claims that. All of quantum mechanics goes against the grain of such understandings, that Newtonian space can be shared. We can explain the illusion why you still can meet people very good with the findings of Buzsaki, but don't see that as proof of Newtonian space. That is quite horrid. A navigation system is only useful as its ability to navigate the body. How does the abstract hippocampal cognitive map instruct the body to choose the right path in this map? The most dense projection of the hippocampus converges on a subcortical structure called lateral septum, which in turn projects to the hypothalamus, the motivational mover of the brain. Indeed, spatial information about the animal's whereabouts is also present in the neural assemblies of lateral septal neurons. Therefore, the lateral septum is an interpreter and translator of the abstract map to motivated action. Very important, motivated action. Allocentric map representation and self-reference or egocentric path integration route information work together. The environmental conditions determine which strategy dominates. In cue-rich environments, representations can be updated frequently by changes in the configuration of sensory inputs. In environments with few stationary landmarks or in complete darkness, like the blind child, path integration is the default mode. Do these map and path integration mechanisms need different neural networks? Or are they different manifestations of the same or overlapping neural substrates? We can only guess that navigation effectively exploits both systems. When the goal is to generate a universal solution, getting from anywhere to anywhere else, maps are superior to route descriptions, provided that landmarks are available. Planning a route within a map requires creating a mental image of the self and its position on an allocentric map. We can gain some insight into how this may happen by looking at how autonomous robots learn to navigate. Navigating robots. Like animals, navigating robots also face the problem of locating themselves in the environment. The breakthrough in autonomous robot navigation came from the recognition that perfecting the robot's senses does not help much with navigation. Senses are useless unless the robot can actively move them while keeping track of the motion-induced sensory feedback from the environment. Once mapping and robot localization were combined into a single estimation problem, progress accelerated. This insight is nicely expressed by the acronym for the solution, simultaneous localization and mapping, SLAM. A combination of motor-driven path integration and sensory-dependent landmark detection. The movement trajectory of the mobile robot and the locations of all landmarks are continuously estimated and updated without the need for any prior knowledge. In the process, the robot can construct a map of an environment by fusing observations from different locations while using the map to deduce its location. The estimation accuracy of the robot's current position is bounded only by the quality of the actively constructed map. The more the robot moves around, the better the estimation of the relationships among the landmarks becomes. Thus, performance improves with exploration. At the conceptual level, autonomous robot navigation is now considered a sole problem, although numerous practical issues remain in realizing more general solutions, increasing speed and accuracy, and generalizing to multiple environments. This spectacular progress in autonomous robot navigation may soon make them part of our everyday lives. A variety of mobile robots have been tested indoors and in outdoor environments where not all landmarks are fixed. Robotic cars must constantly update their position relative to other moving objects. Recent mobile robots can even autonomously navigate through busy urban city centers and interact with pedestrians and pets. These technical developments have gone a long way from the grey Voltus Machina Speculatrix, but fundamental ideas about ambulation-induced knowledge collection have remained the same. If machines with few microprocessors or insects with tiny brains can solve the navigation problem, why do mammals need a complicated navigation system with millions of interactive neurons? To be fair, autonomous robots are not yet perfect, and unmanned cars and trucks strongly depend on global positioning system assistance. Most insects do their business in relatively constant environments, so they do not need to construct many independent maps. Their seemingly astonishing navigation abilities depend on rigid computational rules. Ants and bees can produce directly from one familiar food goal to another by selecting the appropriate long-term vectors and combining them with one another. However, they consistently fail in situations that require explicit comparison between separate maps. The mammalian navigation system not only represents more environmental details, but it can flexibly combine and compare any of those details to symbolize and categorize events, objects, and living things. Internalizing routes and maps for mental navigation. To investigate how such combinatorial abilities may have emerged in mammals, we must recall the dictum, structure constrained function, which is especially true in the hippocampal system. Nothing about its architecture and connectivity suggests that it is evolved for spatial navigation, but nothing else. The expansively parallel granule cell interface and the strongly recurrent CA2 and 3 excitatory system, two very different architectural designs, appear ideal for segregating and integrating places and objects. However, segregation and integration are fundamental operations that could benefit numerous brain processes. Thus, the hippocampal system evolved initially for spatial navigation may be repurposed for other tasks as well. One circuit, many apparent functions. The hippocampus entorhinal system has a typographically organized bidirectional communication with a large neocortex. In a rodent, a major fraction of the neocortex deals with the controlling motor outputs and processing sensory inputs. In primates, in contrast, a large part is dedicated to computing more complex functions. The non-sensory representation in the hippocampus has progressively increased with the enlargement of neocortex during mammalian evolution. Therefore, computation of spatial information might be only a part-time job for the hippocampus in animals with larger brains. This idea suggests that whatever information the hippocampus receives from whichever parts of the neocortex, the same general computation will be performed. In other words, the hippocampus is blind to the modality and nature of the inputs. It processes the messages from the neocortex in the same way, irrespective of their origin, and returns its judgment to the source. Whether it appears to process spatial, temporal, or other information is determined largely by the experimental setup. If the hippocampus served only navigation, it would remain a mystery how I can jot down these lines without any help from environmental cues in Narita Airport, Japan, where I'm currently waiting for my connecting flight. These very same structures are also responsible for seemingly separate functions such as memory, planning, and imagination, of all which must be supported by self-generated cell assembly sequences rather than rely on external or body-derived stimuli. As I explain later, These cognitive functions can be thought of as mental navigation that emerge from mechanisms which were initially introduced for spatial navigation in the physical environment. Forms of mental navigation, starting with the famous patient H.M., who had both hippocampi surgically removed in an attempt to alleviate his intractable epilepsy. A consensus emerged that the hippocampus and associated structures are responsible for making memories. How are memories related to spatial navigation? Another postulated hippocampal function. John O'Keefe, the preeminent promoter of the cognitive map theory, speculated that addition of temporal component to the basic spatial map in the human provides the basis for an episodic memory system. Wow! On the one hand, this suggestion implicitly implies that the hippocampus in rodents and in humans does different things, and that rodents lack a temporal component. On the other hand, it is not at all clear how adding time to a cognitive map, an allocentric construct that depends on external drive, can provide a mechanism for the most egocentric thing we possess, our collection of episodic memories. Perhaps if the navigation system can disengage from environmental or bodily cues, its internalized performance could support memories. Analogous to spatial navigation, two forms of hippocampus system dependent memories can be distinguished. These are personal experiences, that is episodic memory or memory for specific instances, and memorized facts, semantic memory or memory for statistical regularities. We are consciously aware of both types and can verbally declare them, so together they are called declarative memories. Terms such episodic-like or flexible are used to refer to analogous memories in non-human animals. Personal memories are important episodes of our lives that give rise to the feeling of the self and are the sole sources of individuality. To re-experience such first-person, egocentric, context-dependent episodes, we need to project ourselves back in time and space. Endel Tulving of the University of Toronto, Canada, coined the term mental time travel for this hypothetical brain operation. Mental time travel allows us to be aware of the past and the future. Going backward in time is known as episodic recall, while traveling into the imagined future can be called planning. Some people might protest, of course, that the past and future are vastly different, and that this distinction should also apply to memory and planning. Indeed, these categories are typically dealt with in different chapters of neuroscience handbooks and assigned to different brain structures and mechanisms, but the brain may not see things this way. My first proposal to address these problems is that the brain mechanisms that evolved initially for navigation in physical space by dead reckoning are basically the same as those used for navigation in cognitive space to create and recall episodic memory. My second related proposal is that the neural algorithms evolved to support map-based navigation are largely the same as those needed to create, store, and remember semantic knowledge. My third proposal is that generation of semantic, allocentric knowledge requires prior self-referenced episodic experience, akin to map creation by dead reckoning exploration. Semantic memory. In contrast to the observer dependence of egocentric episodic memories, semantic knowledge is observer independent. Semantic memory defines objects, facts, and events of the surrounding world independently of temporal context, similar to how place cells and grid cells explicitly define position coordinates in a map. The deep relationship between physical and mental navigation is also illustrated by the practice of Greek orators. They memorize their speeches by imagining that they walk through different rooms of their house, with each room containing a particular topic. Professional jazz musicians also imagine a landscape of notes and navigate through a pre-planned path in a concert. Unlike the one-trial acquisition of episodic memory of a unique event, semantic information is typically learned after repeated encounters with the same thing or event. initially encoded in episodic memory, information gradually loses its contextual features to become generalized and explicit, reminiscent of the place fields, which are omnidirectional. That is, a place cell fires in its place field irrespective of from which direction the animal approaches it. For example, if you are lucky and discover something, the episode remains precious for the rest of your life. However, if my laboratory and others confirm your discovery by reaching the same conclusion from different angles, it becomes a fact. That is, explicit knowledge understood by everyone in the same general way, irrespective of the conditions of the discovery and confirmation. Not everyone agrees that episodic experience is necessary to encode semantic information. Indeed, in humans, speech and other externalized functions of the brain allow rapid acquisition of semantic knowledge without the need for personal experiences. A caregiver can provide the names of objects, which the child then learns. Patient born without a hippocampus can acquire facts and use them efficiently to communicate. However, even though social interaction can provide shortcuts to knowledge, this ability does not undermine the evolutionary origin of episodic and semantic memory from dead reckoning and map-based navigation, respectively. The relationships among events and objects, known as semantic proximity, shares many features with distant relationships in landmark navigation. Models of semantic relatedness uses a metric based on topological similarity, just like spatial relations among landmarks in the cognitive map. There is a general agreement that declarative memories depend on the entorhinal cortex hippocampal system, although debate persists about the fate of consolidated semantic information. One controversy is whether the neural circuits involved in creating semantic and episodic memories overlap or completely separate. Another controversy is whether memories remain in the circuits where they were created, or move gradually to the hippocampal system to the neocortex over time, so that retrieval of consolidated memories no longer requires the structures that originally created them. The latter idea likely derives from the initial description of the cognitive symptoms of patient HM. According to early analysis, he could not learn or remember new declarative memories, but could recall virtually anything that happened before his brain surgery. However, subsequent work on HM and similar patients reveal that after bilateral hippocampal damage, they cannot narrate and lack the ability to travel mentally either to the past or the future. Their imaginative and planning skills are as strongly impaired as their ability to place themselves into a spatiotemporal context. Instead, they use intact logic and semantic knowledge to invent scenarios that might sound reasonable. And I had to put in a parenthesis. When I read this first, it struck me, this is so close to the one below boss level in organizations, volunteer organizations, enterprise organizations, state organizations. They all locate themselves to ready-made models made by others. This brain damage patient, or no, it's not brain damage, operated patients where he lost the hippocampus, he had the rest of the brain, so everything was accessible, all his memories before the operation were intact, but he could no longer use vivid memories, living memories. Instead, he used semantic memories, the things you can catch from the outside, externalized facts, the second take of the laboratory, or the third or the fourth, once something becomes established. And this is very close to Harry Yuval, that shows that most people today do not use their own abilities. Those abilities are too underdeveloped to be used. Instead, they orientate themselves when they move about, and even more when they think according to utterly constructed models, utterly semantic things, which should be secondary, because you need to orient yourself allocentrically from the inside. But that is not the case today. That is beyond boss level. Over boss level is completely different. It's a whole different ballpark. Very interesting. For example, if you asked about the house where the amnesic patient grew up, you might be impressed with the recalled details and perhaps events. However, the patient remains unable to narrate a single personal episode, such as dinner with the family or a fight with siblings, in the proper sequence. In other words, these patients cannot recapitulate or reimagine a situation by embedding themselves into it. A more recent view, known as the two-trace model, suggests instead that although episodic memories are transferred to the neocortex, a copy of the memory is retained in the hippocampus. In support of this view, functional magnetic resonance imaging, fMRI, experiments in human research participants consistently show hippocampal activation during memory recall, even for events acquired decades earlier. Wow. An alternative explanation is that the memory trace itself no longer resides in the hippocampus. Wow. but that hippocampal networks help to coordinate the sequential recall of items stored in the neocortex, thus providing an egocentric perspective for the items and events of the episode. Overall, comparison of spatial and mental navigation indicates how disengagement of navigation networks from their external dependence could transform them into internalized memory operations. This recognition simplifies our understanding of neural mechanisms of apparently different functions. While spatial navigation, memory, planning, and imagination are distinct terms, their neural substrates and neurophysiological mechanisms are identical or at least similar. Viewed from the brain's perspective, these distant chapters of behavioral neuroscience and psychology can be unified. The serendipitous discovery of these mirror neurons is arguably one of the most celebrated moments of cognitive neuroscience in the past century. Giacomo Rizzolatti and his colleagues at University of Parma, Italy, observed that some neurons in the pre-motor cortex of macaque monkeys fired not only when the monkey performed a particular action, such as picking up a peanut with its fingers, but also when it watched another monkey or the experimenter performing the same action. Observing the robust responses of these neurons leaves no doubt that they are special, and they represent a wide range of actions. In a small subset of mirror neurons, the correlation between the observed and executed actions is strong, both in terms of general action, grasping, and the executed action, the precision grip. However, most neurons in the premotor area display a reliable correlation between the visual action they respond to and the motor response they organize. Mirror neurons catapulted to fame after their indirect demonstration in the human brain. College students watched experimenters make finger movements, and in some trials made the same finger movements themselves, while their brains were monitored by fMRI. During both observation action, and observation-only conditions, activity was seen in two areas. The inferior frontal cortex and the rostral-most part of the right superior parietal lobe. Similar activations were observed and participants imagined movements instructed by symbolic cues. Although both brain areas participate in action imitation, their roles are somewhat different. The opercular region represents the observed action as a motor goal or plan. Without defining the precise details of the movement. In contrast, the right parietal lobe represents the kinesthetic details of the movement, e.g., how much the finger should be lifted and in what direction. If these areas respond equally well to the real and observed or imitated actions, how do people know if they are the actor or the imitator of movement? One possible answer is that the signal in the parietal cortex reflects a corollary discharge copy of the planned action, creating some firing patterns, differences between real and internalized actions that can inform the brain that it is my body that is moving. Extracellular recordings of neurons in human patients shed some light on such subtle differential patterns. A significant fraction of neurons in the supplementary motor area and even in the hippocampus respond while patients either execute or observe hand-grasping actions and facial emotional expressions. Some of these neurons were excited during action execution, but inhibited during action observation. These findings are compatible with a mechanism that differentiates the motor and perceptual aspects of actions performed by self or others. The original mirror neuron studies examine the similarity of neuronal patterns between performing actions and watching others perform actions. Subsequently, this idea spread to other areas of neuroscience. As researchers investigated how such neurons can encode other people's feelings, intentions, and emotions. When we say tarantula crawling on someone else's chests, are the same type of neurons in the same brain regions active in both the observed person and the observer. fMRI experiments suggest so, at least in the secondary somatosensory area. The mirror neuron system may link an action and its meaning or intent, whether the act is committed by yourself, by others, or even by simulation in the mind. the action of these neurons may form the neurophysiological basis of some aspects of our social interactions. The brain's disengagement from overt movement has important consequences. First, during internalized states, the motor system puts the action planning in a motor format, so that it looks like a real action when related to recorded neural activity, even when it is not accompanied by overt action. From this perspective, imitation can be regarded as a transformation of observed action into an internal simulation of that action. Second, the corollary discharge signals to parietal cortex resulting in covert actions would allow the brain to evaluate the potential consequences of future plans. Without any overt behavior, the mirror and corollary discharge systems can then inform the brain's owner that she is the agent of this covert action. Social interactions are actions. One of the most elaborate corollary discharge systems relates to eye movements, which allow a newborn to begin to discover the world long before reaching and crawling developed. Faces and biological motion are especially effective in triggering eye movements in visual animals such as humans. There are at least two ideas to explain this. One view is that these cues are somehow special for the brain, so they automatically trigger a response. Another view is that eye movements reflect internally driven seeking for ethologically relevant patterns, so the brain can make adaptive use of those cues. Although the distinction may seem subtle, the answers may determine how we search for and evaluate the underlying mechanism. Monitoring eye movements in the laboratory tells us about the brain's engagement with the world. This simple method does not require verbal communication. Alteration of eye movement patterns can be diagnostic for neuropsychiatric diseases, most prominently autism. Autism is usually defined not by its underlying mechanisms, but by impaired social communication and repetitive behavior. One of the first things parents discover is that autistic children rarely solicit or reciprocate eye contact with caregivers, unlike normal infants. This difference becomes apparent by 2 to 6 months of age. There is nothing wrong with the eye movements in affected children. They simply look elsewhere. There is no large gap between autism and many odd but healthy people. Instead, there seems to be a continuum of sociality reflected in the amount of social visual engagement, which is largely determined by genetic factors. When identical twin toddlers viewed movies of other toddlers interacting, they tended to fixate their eyes on similar things. Moreover, they shifted their eyes at the same time in the same directions. In other words, their eye searches were remarkably concordant. Such joint patterns were much more rare in sex and age-matched non-identical twins or non-siblings, showing that it is not only the movie scenes that synchronize the eye movements patterns in identical twins, but also some internal programs. Heritability of eye search is most prominent in gaze towards the eyes and mouth. Toddlers with autism rarely focus on these critical parts of the face, so they do not learn about social consequences of their actions from smiles and grimaces of other children and caregivers who try to engage them. Investigate the white of the eyes. These findings, admittedly selected with some bias from an enormous literature with various and often conflicting views, suggest that internally driven seeking of face cues is heritable. The neural mechanisms responsible for social visual engagement are not well understood. But if I may speculate a bit, the amygdala is likely to be a key structure. The amygdala and its partners comprise a neural system involved in the perception and expression of emotions and the retrieval of social cues from facial expressions. Nearly all social interactions involve emotions. Patients with complete bilateral amygdala damage have difficulty judging people's trustworthiness based on their appearance compared to people with intact brains or control patients without amygdala damage. People with bilateral amygdala damage also cannot recognize fearful faces. These results, along with numerous experiments in animals, have been interpreted to indicate that amygdala is the seat of emotions, particular fear. But this textbook teaching may be misleading. First, the impairment of emotional face judgments does not extend to verbal description of people. Second, in contrast to the laboratory, where emotions are tested by viewing still faces, patients with amygdala damage do not necessarily misjudge untrustworthy persons in real life. Third, they easily recognize fear expressed via vocal communication. Fourth, when they are instructed to focus on the eyes in the pictures, the judgment becomes close to that of control subjects. Both the clinical findings and the animal experiments are compatible with the alternative interpretation that the amygdala's main behavioral function is to direct the gaze to cues that are ethologically relevant for social communication. For primates, these cues are mainly aspects of the face, including the ears in monkeys. Physiological experiments support this idea. There is a general consensus that the inputs that are physiologically relevant to neurons should induce robust firing. However, neurons in the amygdala are infamous for firing at extremely low rates under most circumstances, including fear conditioning experiments. Perhaps the experimental conditions that lead to fear learning are not really what the amygdala neurons care about most. But similar to other neurons in the brain, amygdala neurons can also become very active under the right circumstances. In an illuminating experiment, neural activity from monkey amygdala was recorded while monkeys viewed videos of natural behaviors in unfamiliar monkeys. When the recorded monkey made eye contact with the video monkey, the firing rates of many neurons increased several-fold. When the gaze of the movie monkey pointed instead to the peripheral parts of the recorded monkey's retina, only a small response were observed. A critical observation was that the firing latency of these gaze contact neurons varied between 80 and 140 milliseconds, which is tens of milliseconds shorter than the response latencies to visual stimuli. This experiment therefore suggests that amygdala neurons do not respond to a particular visual pattern, but may be involved in selecting which parts of the face should be consulted when examining strangers. Well, it goes to show that the finer details in the face are so important. So even if the gaze of the autistic child might look similar to even the parents, not locking gaze will mean the whole difference. It would be a whole other world for the kid, losing out on every information or knowledge from the parents and looking elsewhere into I would say, I think there's a connection here to E. McGilchrist, because autism is progressing. It is a new thing. And I think it is the same error of classical mechanics that makes these children look out in the world, looking for the information or the connection there. And something is already wrong, because I think it's a 10 doubling of autism the last century. That is quite amazing. And there are cues already in the parents how their external surface, the projected surface, the one you can't see, do affect the children already in the natal state, the prenatal state. And those effects, they turn out to be these things in the end. I think there are good indications of that. A person that is autistic can make a child scream if it's not used to that. Very, very different touch. The whole system is different, and it's also noticeable from a distance. It is nothing internal about it at all, and internalization is part of classical physics, and strong borders between inside and outside. Those borders are penetratable, and they need to be. It seems that the autistic child, with its different gaze, well, the gaze is similar. It is a gaze that is similar to the gaze of post-Iliad and post the Odyssey. Why? Because before we know they were not looking out in the world in the classical way. All their gazes had different names, and all the internal states had different names, and they varied during the days, during the weeks, in different interactions. And in the end, it became objects outside. And they took, after the Aeonian philosophers of nature, they took a dominant part. They became what made up the world. And therefore, these babies look outside. And I think Ian McGilchrist also took up how, in a way, absurd is the idea of hereditary autism. Well, it's hereditary in the way it's transformed from the parents, most likely, but not in a genetic way. And how absurd that they never explain the exponential rise of autism in modern time. It goes hand in hand with schizophrenia, which is quite different, but I would say it's a different take of the mechanical error. The mechanical error is not an ideology. It is not a specific way of understanding the world. It is obvious from György Buzsaki, it's a way of not understanding the world. And none of these people share anything. They share their problems maybe in an explicit way, but there is nothing to classical mechanics in that way. You cannot perceive it or experience it. You are just making mistakes. And I'm quite certain that the mechanical space will also affect your planning capabilities, as explained by Hari Yuvari, that most people today cannot plan. Instead they take down external semantic modes, meanings, put them together, call them episodes, and they compare them. And that could work, but we know it works to a very low degree. And the success is not promising. It's very down-putting. This is the reason that people do these things, and in the end they're just chance. It's a horrendous way. But thank God most people don't regulate their own lives. It will be an absolute disaster. And this was proven or showed that the whole world will erupt in chaos if people decide for themselves. People are more led today than ever before, because even their space and time is regulated by others. It goes for they at least have some planning. I do my summary now. I'm just gonna read some few words here. I stop there and continue my summary. This is the neurological Wittgenstein. This is to show that we learn our concept by doing them, and there is always a degree of understanding something better and better and better. There is never ever a 0 and 1 perspective. It is not Google Translate. Less than you are in the world, you can never know the intention of, let's say, some 5 sentences. Everything changes. And one of the clues for Wittgenstein was, of course, the gesture from the Italian professor. What is the correspondence of this? A very familiar Italian gesture. It's both action semantic, and it doesn't point to something in the world. That scary early Wittgenstein, who thought that everything came from the outside, and his gaze was different in the beginning. It was almost the gaze of a weird person looking for the object somewhere out there, trying to gather information, understanding the world. It also goes to show that we constantly train ourselves to understand words. And most people today, they use words. I do myself, we all do that, because there are way too many words and way too little time to understand how to use them. And the progression means that we don't train. So we get a big vocabulary without understanding the use of the words, or a very low understanding of the use of the words. Something I recognized in my lectures when I had people asking, does, for instance, this question came up like 4 or 5 times, does the world not follow the Popperian idea of falsification, which is it's an imitation of what is Popper. It is a grammatical error to say that. It is not what he means. But they caught up the words and they put them together and sort of revealed themselves using them wrongly. Like saying, I was swimming in a car. That would be, I don't know swimming. And the more I don't know swimming, I could say I was swimming in a car. Maybe I've never seen a lake. That's those people living in the desert and don't know what swimming could be. So this is happening more and more. And I think the modern educational system not bringing the bodies in, thinking that the work was already done by our predecessors, our ancestors. They did a tough job of developing the semantics, as Buzsaki calls it. So we can just give it to the new children. Buzsaki shows that to be wrong. We need both the words and the actions. They cannot be telepathically transferred. We need to do them. We need to learn how to play the harp before knowing the different technical expressions with the harp, with what it could be, and a technotheo, those expressions. We need to do music before we understand moll and dur. We don't understand that also. We can't see what an octave is if we never played. So we need to play first, and then we can take slowly use of the expressions. And this was actually the point also of Paul Feyerabend of science. He was the only philosopher of science who worked in close connections with scientists, especially at CERN and other very advanced things. And his proposed theory is a defense of science, but for most people it sounds like an attack. Why? Because it says, don't give the semantics if you don't have the practice. And still to this day, even when we discover the Higgs boson, that is done in CERN, manually, by eyes and hands, not by the ones explaining it later. Yes, they might be the instigators, but it's still done in a connection between man and machine, deep down in the cellar in Switzerland. It hasn't left the world, it hasn't become transcendental, which I think is a rather happy message of Paul Feyerabend. It's odd, he was the only one who was working extensively, being at the spot, being practical himself, who was accused of attacking science, being a scientific anarchist. And this goes to show that the stale, static science we have today is not only, as Paul Feyerabend, rightly so, I think, is strangling itself, it's also strangling everyone else by, without unthinkingly, reinforcing the old gestalt of classical physics, which is a not knowing. It is not understanding what time and space is. It's a non-understanding of time and space. And oddly enough, therefore, the title of the book, Julian Barber, should not be the end of time, but the birth of time. I say thank you very much. Sorry for the long distance here. I hope everything got neatly recorded.